A rotary encoder is used to navigate through the menu system of our sensor hub. The rotary encoder features two square wave outputs which are used to calculate the rotational direction of the encoder shaft. Since both outputs are 90 degrees out of phase, a signal comparison is made whenever there is a signal change. When the signals of the two outputs have opposite values, the encoder is rotating clockwise. When they match, counterclockwise. The rotation direction is translated in the menu system to be up and down to navigate through the sensors. The FPGA will also light up two of the small LEDs on the board indicating the direction of rotation. So the LED on the left will light up when it's turning counterclockwise and right during clockwise. The push button on the rotary encoder is also used to enter and exit the sensor data submenus. Both the push button and the shaft of the encoder have their own separate debus modules to prevent false user inputs.
The LM75A digital temperature sensor is built into the FPGA board. The sensor has an integrated analog to digital converter and utilizes I2C interface, supplying temperature readings to the I2C master for values between -55 degrees Celsius to 125 degrees Celsius. The Verilog code comprises of an I2C master module which controls the sending and receiving of data to and from the sensor. 400 kHz clock pulses are sent to the sensor via the SCL line, while data is transferred via the SDA line. The temperature data comes in two separate bytes. However, for simplification, the polarity was assumed as positive and decimal places were discarded for this project. This allowed us to store the reading as a single 8-bit register, which would be much more easily received by the 7-segment display module for displaying to the user. The reset button can also be pressed to restart the entire communication process with the sensor.
The Sharp GP2Y0A2 infrared distance sensor has an analog output with a 5V reference. It interfaces with the FPGA through the ADC IC MCP3008 using 4-wire SPI protocol, which serially outputs a 10-bit value. The ADC module works based on a finite state machine where there's a set number of states it can be in. Chip selects must be driven low while communicating and pulled high again between communication. On a negative edge, the configuration bits are sent to the IC, which selects channel 1, followed by the data bits, which are shifted out. The data is then reset and the process starts again, after chip select is pulled high and then driven low again. Additionally, the 10-bit value is then passed through a 10-digit binary to 16-bit BCD converter to the SSD. The SSD value displayed is in its digital value, which has not yet been converted to distance. A digital value of 512 is equal to approximately 20 centimeters, and decreases as the distance increases.
The HC-SR04 ultrasonic distance sensor uses digital logic to calculate distance from an object. The distance sensor features two logic pins, which is the trigger and the echo pins. The FPGA will pull the trigger pin high, which causes a pulse of ultrasonic noise to come out from the transmitter of the sensor, and then it will hit an object and return back to the receiver. Once the pulse has been received by the sensor, it will then pull the echo pin high. We have used a counter to count the amount of time between the trigger pin and the echo pin going high, and then just use a simple formula to calculate the distance. The distance displayed on the FPGA is in centimeters.
The fourth and final sensor connected to our hub is the PAJ7620 hand gesture sensor. This module operates over I2C and outputs an 8-bit value that indicates what kind of gesture it is currently seeing. And as you can see from the footage, it's currently not working correctly. This is primarily due to the sensor having no volatile memory, which means nearly half a kilobyte worth of data needs to be uploaded in it first every single time the board powers on. Due to very poor manufacturer's documentation, this was only discovered at the last minute and was deemed too difficult to implement given our timeframes. Nevertheless, the system itself works by sending out two separate packets in order to query a specific register for data called flag 0. Without going into too much detail, this requires 4 separate modules to perform timing corrections, packet generation, and data collection. Using a 5th module, the data received from this register is then latched for 2 seconds at a time so that it can be more easily read by the user without any screen flickering. Due to the specific timing constraints on the IC, this is the only subassembly which runs on a 1 MHz clock, as opposed to the rest which run directly off a 50 MHz crystal.